Hi, hello, and welcome. I'm Greg Jacobs. I teach at Woodbury Forest School, a country club for dogs in Central Virginia. Or at least that's what our empty campus feels like in the evenings as the faculty take their nightly dog walks en masse. It's a mass of dogs. Usually, though, the dogs are far outnumbered by 400 boys living in dorms, and I long for those usual days to return. Okay, we know what kinds of problems you are going to see on the AP Physics 1 exam on May 14th. The second problem will have a 15-minute time limit and will ask you in large part to respond with, quote, a clear, coherent paragraph-length response. Think of that the same way you'd think of a justify your answer question. Just you're going to use about 5 sentences instead of about 2. On the other hand, the first problem will have a 25-minute time limit, and it will be a qualitative-quantitative translation. Think of that as just a normal physics problem, but one unlikely to use numbers. You'll be asked to relate algebraic expressions to physical behavior. That is, here's some math, here's an experiment, explain what features of the math explain the behavior of the experiment. Notice that I said experiment. Wait, you say, I thought the experimental design question wasn't on the 2020 exam. It's not. But every physics problem that can possibly be posed must be based on a real experiment. Otherwise, it would be a mathematics problem, not a physics problem. See, that's what physics is at its very heart, predicting how the natural world behaves using mathematics. So don't be surprised when the first question asks something like, what would happen if we increase the cart's mass? What would happen if we increase the cart's mass? Explain without using equations. You will have to use your experience along with a conceptual understanding of physics principles to imagine and describe how an experiment would behave. How do you prepare for this kind of question? By doing the kinds of problems that Josh and I are setting up on these shows. Not just what is the value of the cart's acceleration, but also how would that acceleration change and why? Explain in words how you determined the cart's acceleration. And even, what does an acceleration of 4 meters per second squared mean about the motion of the cart anyway? In other words, just do physics. The format of the exam will allow you to express your deep understanding. And now, let me show you what we're going to be talking about today. I'm going to start with the question from Tuesday. Josh posed one, and then we're going to do a lot of experiments with a cart, with moving masses, and eventually with Edna and Bertha. Let's start with this guy here. This is what Josh showed you yesterday. It poses a problem with a block being pulled by a string. The string's tension is kept constant at 15 newtons. There is friction, and they ask us to explain why the acceleration isn't what they say. I'm going to start with part B. Are you allowed to start with part B? Of course. Who says you can't? Part B asks for a free body diagram for the moving block. So here's the dot. What forces act on the block? We start with gravity. Gravity always acts down last I checked. That's the force of the Earth on the block. Everything else must require contact. What else is in contact with the block? Well, the track. The track is applying 2 forces in this case. A normal force perpendicular to the track, the force of the track on the block. And since the problem said there was a coefficient of kinetic friction and the thing is being dragged, there is a force of friction. Since in the original problem, the string was pulling to the right and the object was moving to the right, the frictional force has to be to the left. That's the force of the track on the block. What else is touching the block besides the track? The string. So the force of the string on the block. We don't write 15 newtons, we write a variable that represents the force of the string on the block. What else is touching the block? Nothing else. So that's our complete free body diagram. In the vertical direction, the block was in equilibrium. That is, the block was neither pushing into nor lifting off of the surface. Therefore, vertically, up equals down. Horizontally, there was acceleration. The acceleration was to the right. How do I know that? Because the block was speeding up and moving to the right. Therefore, in Newton's second law, we write net force is mass times acceleration. The net force is the right minus the left forces. How do I know that the net force isn't left minus right forces? Because we always start in the direction of acceleration. So I will write there's my equation. I did that without even thinking about what the problem is asking. Now let's go back to part A. Part A asked, why isn't the acceleration the 15 Newton tension force divided by the mass of the block? Well, now it's obvious, because the 15 Newton tension force is not the net force on the block, and only the net force can be set equal to MA. The net force is the tension minus the friction force. That's your full explanation. That's all we need to know. Briefly explain means explain in one sentence. I just did. All right. That's enough of that problem. Let's do a similar problem. I have here a cart on a track. It's attached to a string. The string is passing over a pulley. It's a very light pulley, very light and frictionless pulley. And there's something hanging down here. And I'm going to tell you, when I release this, the cart will speed up to the right, to your left, speed up to your left. And I want to know, what will the acceleration of this cart be, knowing that when I let go, the tension in this rope will be 1 Newton, 1.0 newtons. 1.0 Newton tension, and the mass of this cart is 250 grams. Okay, that's still a one-body problem, a one-object problem. So let's draw one free body diagram and solve from there. Here's a free body diagram of the cart. Cart always has a weight. What else is touching the cart? Only things that are touching the cart can apply a force to the cart. The track is pushing up, the force of the track on the cart. There's no friction in this case, because this is my special cart on my special track where it has wheels that have minimized friction. Whenever I'm using this cart on the track, friction is negligible. If you have a smooth track, don't put friction in. What else is touching the cart? The string. The force of the string on the cart. What else is touching the cart? That's it. So this is my complete free body diagram. In the vertical direction, we know that Fn equals mg because we're in equilibrium vertically. The cart is neither burrowing into the track nor lifting off the track. Horizontally, the cart is speeding up to the left, therefore the tension or the net force is to the left, and therefore we can write that the tension is equal to the mass of the cart times the acceleration. The acceleration then is the tension in the rope, which I said was 1.0 newtons, divided by the mass of the cart, which is 250 grams, so 0.25 kilograms. And if you divide that out, you get 4 meters per second per second. Let's check that out. That's hopefully correct. I am going to share. And you can see that I have a velocity time graph that I'm going to make. The slope of a velocity time graph is acceleration. So first, let's make sure that we are collecting data. Yep, you can see that, right? Now I'm going to let this go. We'll find a velocity time graph and we'll take the slope of the velocity time graph to determine the acceleration. Slope of the velocity time graph looks like it's 3.9 meters per second per second. I said 4 meters per second per second. Physics works. I like it. All right. Now I'm going to ask a question of you. One thing I didn't mention is, how did we get that 1 Newton of tension? How did I arrange for this string to always provide 1 Newton of tension once I let go? Okay. What I did was I had a hanging object. It's down here. Come on. Here's the hanging object. that was right over here, and it pulled. So please write down somewhere, just write down on your computer screen, anywhere you want. How much mass did I have to apply here in order to get a tension of 1 Newton? You can answer in kilograms and grams, it doesn't matter. How much tension did I have to apply to get a 1 Newton, or how much, I'm sorry, it was a 1 Newton tension. How much mass did I have to hang here to get a 1 Newton tension? Write it down. Commit to your answer one way or the other. It's okay if you're wrong. All right. Let's answer. I know a lot of you said, well, 1 Newton is equal to the weight of the hanging stuff. 1 Newton then is mg. G is 10 newtons per kilogram. So I've got to have 0.1 Newton or 0.1 kilograms of mass, which is 100 grams, right? Well, let me share with you, let me just show you. This is 100 grams. This is more than 100 grams. This is 70 more grams. This is 100 grams. This is 70 grams. I had 170 grams, not 100 grams hanging there. But wait, didn't I say that the tension in the rope was 1 Newton? How did I have 170 grams producing 1 Newton of tension? That doesn't make any sense, but it does. This is a two-body problem. This thing was speeding up downward. This thing was not in equilibrium, so the tension in the rope was not equal to the weight of this thing. Let me show you how to solve two-body problems. I'm setting this up again for you. To solve a two-body problem, there are 2 different approaches that we can use. The first approach is to draw 2 separate free body diagrams, one for each object. We've already drawn the free body diagram for the cart. I called that in my little picture here, object 1. So I'll put a little M1 there to indicate that I'm talking about the mass of object 1, 250 grams. But now I'm going to draw a second free body diagram for the hanging thing. What does the free body diagram of the hanging object look like? Well, gravity. I call that M2G because that's a different weight than the cart. What else is touching the object? The rope. The rope is pulling up. These are the only forces acting on the hanging object because nothing besides the rope is in contact with it. So now I have 2 free body diagrams. Therefore, I write 2 expressions for Newton's second law. Newton's second law says that net force is mass times acceleration. Net force is defined as left minus right forces, or up minus down forces, or down minus up forces. How do you know which way to go? You start in the direction of acceleration. Since this cart was moving left and speeding up, we start with the left forces minus the right forces, and we write t minus 0 equals ma, where a is the acceleration of the cart, and this is m1 because we're talking about the cart's mass. Over here, which way was the acceleration? The hanging object was moving down and speeding up. When an object speeds up, its acceleration is the same as its direction of motion, so its acceleration is down. Therefore, I start with down minus up forces. So a question you all have, I already answered, why didn't I do t minus mg? Because I started the direction of acceleration. Notice there's no negative signs here. There's no direction that is positive. It's just you always started the direction of acceleration. That solves all your sign issues. Why did I use subscripts for the masses, m1 and m2? Because these are 2 different masses and I have to differentiate them when I am solving this problem. Okay, Greg, then why didn't you put subscripts on the tensions and the accelerations? Because, and this is generally true for most two-body problems, when 2 objects are stuck together or when they are connected by a taut string, they have the same acceleration. Why is that? Well, the acceleration means the change in speed every second. So let's imagine that they didn't. Let's imagine that this thing gained 1 meter per second of speed in 1 second, and this thing gained 2 meters per second of speed in that same amount of time. Well, then the string would break. They would go apart. They wouldn't be attached together. 2 objects that are connected together share the same acceleration. So I just used A, not A1 and A2. Okay, what about the tension? Jacob's law of tensions. Jacob's law of tensions says that one rope equals one tension. There's the rotational corollary or the physics C corollary that says unless interrupted by a mass, if I have a rope that goes across a massive pulley or another massive object, then it can have two different tensions. But unless we have that rare case, the tension in the rope is the same throughout. Just use one variable for tension. All right, so now my question for you was, what is the hanging object's mass? That's mass 2. That's what I'm looking for. Do I have enough information to solve? Well, let's see, I don't know that. I know G. I know the tension in the rope was 1 Newton, and I know the acceleration was 4 meters per second per second. The physics is done. Everything else is just plugging numbers into the equation, which is not likely to be something we do on the exam. I did plug these numbers into the equations before we started, and sure enough, you get M1 equals 0.17 newtons. And I want to share the screen with you to show you. I want to show you something cool. Let's go to a force graph of the same experiment that we did. Look here, let's see, there it is. I didn't zero the probe, so that's not going to work. I'll do it again. Here's what I'll do. I'm going to zero my probe, and I'm going to run the same problem, and you're going to see zero force. Okay, so notice it reads 0 force. Now, this thing reads, and you can see it right down here, about 1.7 newtons, because that is the tension in the string before I let go. But watch what happens when I do let go. Come on. When I let go, the force reading dropped from 1.7 newtons to 1.0 newtons or 0.98 newtons. Physics works. I did use a tension of 1 newtons, even though I had 1.7 newtons of weight attached to the object. Okay, a couple more interesting problems with this setup. First question. I'm going to reset this guy, and this time I'm going to have the thing move in a different direction. The cart is going to be given an initial shove to your right. Don't want you to see this happening, so I'll stop the share. This time, I'm going to give the cart a shove like this. And I want to know, will the acceleration, the magnitude of the acceleration, be greater than, less than, or equal to the 4 meters per second we got before? And I want to know right, not while I'm pushing it, but right now. After I push, but before the cart stops. All right, let's see here. Two-body problem again. So let's draw 2 free body diagrams. Let's start with the cart. It's over here. What forces act on the cart? Well, we still got the force of the track, the normal force on the cart. We still have the force of the earth on the cart. The string is still pulling to the left. What else? Well, wait, what's touching the cart? The track and the string. Well, doesn't there have to be a force pushing that way for the cart to move that way? Nothing's touching the cart going that way. Wait, Greg, didn't you touch the cart? Didn't you have to give the cart a shove? What about the force of your shove? That happened before I snapped my fingers. That happened before I cared about the acceleration of this cart. You don't put a force that existed before you're considering something. That happened a long time ago. We only consider the forces acting now. What about the force of motion or the momentum? Those aren't forces. A force is a push or a pull. A force requires contact between two objects other than gravity. What is touching this thing after I let go other than gravity? The answer is nothing. Therefore, there is no force acting to the right in this case. Banana, nana, nana. It's not good enough to know how to spell banana. You have to know how to stop spelling banana. That's the full free body diagram. Similarly, the free body diagram is the same for the hanging object. Therefore, with the same free body diagrams, we have the same acceleration, even when this thing is moving this way. Won't the acceleration change directions? No. The velocity will change directions, but on the way this way, the cart will slow down. When an object slows down, acceleration is opposite the direction of motion. This way, the object speeds up. When an object speeds up, the acceleration is the same as the direction of motion. So the acceleration is always, always, always this way. You don't believe me? Let's check it out. Velocity time graph. Yep. And here we go. Look at that. Look at that. We have the same slope as we had before. And it's 3.9 meters per second, just like we predicted. That graph has a straight slope, which means the slope of a velocity time graph is acceleration. The acceleration is 4 meters per second everywhere, even when the object was moving to your right and even when the object was moving to your left. Isn't that beautiful? All right, one more problem to do with this setup. All right, this is a low friction surface. This is a low friction pulley. Let me take this off for you to see it better. This here, this is a low friction pulley. See how it just doesn't stop? It's also a very light pulley. See how easily I can twirl it. This is a more massive pulley. This one, it is still low friction, but it's very massive. It's heavy. I'm going to use this guy. Now, you might not be able to see it so well. It's going to take me a moment to get set up here. I'm doing this live as always. Okay, now you can't see this other than maybe out of the corner of the frame, but that red pulley is what's rotating right now. And I'm still connecting here. And the question is, what can we say about the acceleration now that we're connected to the massive pulley? That's going to lead us into the second way to solve two-body problems. In the second way to solve two-body problems, instead of drawing two separate free body diagrams, one for each object, we draw a single free body diagram for the system. We draw a single Newton's second law equation for the system. Newton's second law says acceleration is net force divided by mass. When we're dealing with the whole system approach, you write that over here where you can see it. We're talking about the net force on the system of two objects, not on the individual carts, but on the system. And we're talking about the mass, not of the individual carts, but of the system. Well, that's easy to find the mass of the system. The mass of the system originally is m1 plus m2. The net force on the system is just the weight of the hanging object there, which was 1.7 newtons. We called that M2. That was the acceleration of the system in the first place. Some of you are going to have a hard time understanding what this net force on a system means because you can't exactly draw a simple free body diagram for the system. Suffice it to say that the tension in the rope isn't an external force on the system. Only the force of the earth on that thing is an external net force on the system, because the force of the earth on this thing is counteracted by the normal force. If that's too complicated for you, don't worry about it. Just do the two free bodies and the two equations, and I'll show you in a moment how those will simplify to the same thing here. But if you can see this, then you'll understand that for the system, if I add that massive pulley, the net force on the system stays the same, because the only thing that is causing this cart and this hanging object to speed up or slow down is the force of the earth on this hanging thing. That's the net force. But now the whole system has a bigger mass, not just M1 plus M2, but plus mass of the pulley. So we get a bigger denominator, same numerator. That means we should have a smaller acceleration. When I connect to the more massive pulley, I should get a smaller acceleration. Do you believe? Let's check. Let's take a look and see. So we had a slope of, in the original, we had, wrong one. We had a, that's right here. The original, we had a slope of 4 meters per second. Now we have a slope of 3.2 meters per second, 3.3 meters per second. The slope went down. Therefore, the object had a smaller acceleration. Isn't that cool? Okay, 2 more little problems for you. Stop the share. First, I have here 2 100-gram objects. Well, they're in equilibrium, basically. They're moving at constant speed, or they're just still. I'm going to now put an extra 10 grams on this side. So what I've got, if I were to draw it out on an AP exam, would be a pulley. We'll call this one object 1, this one object 2. Object 1, it has a mass of 100 grams, so 0.1 kilogram. M2 has a mass of 110 grams. And the question is, what is the acceleration of the system? I'm going to solve that for you 2 ways. The first way is the way that I suggest if you are new to two-body problems, or if you're uncomfortable trying to imagine the net force on this system, because this way you will always be right. You draw 2 free body diagrams, number 1 and number 2. Object 1 is this guy. No, it's this guy, the 100-gram. M1 is the 100-gram object. There we go. There we go. 100-gram object on the left. So M1G is the weight of the object. What else is touching this object? The string. What else is touching this object? Nothing. Those are the only forces. Object 2 has a weight, M2G. It's touching the rope. What else? No other forces. No other contact. Let's write Newton's second law for both of these. The only trick to this is to understand the direction of acceleration. If I let this thing go, this object speeds up upward, so its acceleration is upward. Notice this is not a force. This is not something you draw on the free body diagram. I'm only writing this direction of acceleration off to the left so that we can all understand which way is the direction of acceleration, so I know which way I should start my Newton's second law equation. Since acceleration is upward, I write up minus down equals ma. Over here, this object, if I let it go from rest, it moves downward and speeds up. When an object speeds up, its acceleration is the same as the direction of motion, so this guy has a downward acceleration. Therefore, I start with down minus up forces. I have 2 equations. Can I solve for acceleration? Well, I don't know the tension, so I can't just solve one equation for the acceleration. I do know the mass, I do know g. What about this equation? I don't know the tension, but I know g and I know the mass. So I have two unknown variables, but I know everything else here. Two equations, two variables is solvable. Therefore, the physics is done. And on one hand, there have been plenty of AP problems that say, write a system of two equations that could be solved for the tension and acceleration. This right here might be the end of your problem. Just say, hey, I have two equations and two unknowns. The problem is solvable. That's good enough in a lot of cases. I want to do the solution because I want to test this with my setup here. I want to do the experimental problem. So the technique we use to cancel out the tensions is, it's very simple. Just add the two equations, stack the two equations on top of each other. The other one is this one. If you do this right, then when you add the two equations together, the tensions will cancel. This tension minus this tension goes away. I get M2G. There's a minus M1G equals M1A plus M2A. Now I have a single equation that I can solve for acceleration, knowing the masses and knowing G. Physics is truly done now. And when I did this beforehand, I got 0.1 newtons over 0.21 kilograms, and I got 0.48 meters per second per second. Let's see if that's right. Share the screen with you. We're going to do a new experiment. So you see, I'm doing this live. There it comes. You can see it now. I'm doing this live. I'm hooking up not the cart, but the rotary motion sensor now. And I want to measure acceleration. Let's try it. Look at that, just below the 0.5 meter per second mark, physics works. Is there another way to get this acceleration value? That's a lot of math. Oh my gosh, that's a lot of math. That's as much math as you should ever do on an AP Physics 1 problem. And if you do any more than that, it's too much. And even this is an awful lot. So is there a way to just get rid of all this and do this a simpler way? Remember, I told you that you could address the entire system instead of trying to address each individual object. It's harder to picture, but if you can, the acceleration is the net force on the system, the net external force on the system divided by the mass of the system. Well, that's easy in terms of the mass of the system. That's 100 grams plus 110 grams, so that's 0.21 kilograms, 210 grams. The net force on the system, well, there's 0.1 Newton of weight that's pulling the system this way. There's 0.11 newtons of weight, that is 110 grams equivalent, pulling this way. So the net force is provided by the Earth. The Earth pulls 0.1 newtons this way, 0.11 newtons this way. So the net force is 0.11, or it's 0.01 newtons this way, or 0.1 newtons this way. You have to subtract the two. I said it all wrong. There we go. Let's just write it out. 1.1 newtons this way, 1.0 newtons this way. Subtract the two, you get 0.1 newtons over 0.21 kilograms equals 0.48 meters per second. Why would you do it this way? Because look how much quicker that is and look how much less math that takes. Why wouldn't you do it this way? Because it might be hard for you to conceptualize why the net force is 0.1 newtons here. why we can subtract this weight minus this weight. You can't just draw a free body diagram to show that. So if you need the free body diagrams, do the first way I taught you with 2 free bodies and just stack the equations. All right, final experiment for you guys. I know it's 12:42, but remember we took about a 5 or 10 minute wait at the beginning. So I'm going to keep going here, and we'll be able to take your questions if you want to give me a question at Jacobs Physics, and I'm happy to have some improv at the end. Last thing we're going to do is a 2-body problem with no pulley. This is Bertha. Say hi to Bertha. This is Edna. You all know Edna. Bertha is going to give Edna a ride. That's what elephants do. Edna is going to ride on Bertha's shoulders. I'm going to pull Bertha to your left on this surface that is rough. It has a friction coefficient with Bertha. We're moving at a constant speed. I want to know what a free body diagram of Edna looks like and how much horizontal force is being applied to Edna in order to keep her moving at constant speed to the left. Everybody understand the question? I'm talking about Edna. I want to know how much force does Edna experience and in which direction to keep her moving at constant speed to the left. This is still a 2-body problem. The 2 bodies are Bertha and Edna. The easiest way to approach this then is to draw 2 separate free body diagrams, one for Bertha, one for Edna. Bertha has a weight. I'll call that MBG for the mass of Bertha times G. What is touching Bertha as she moves at constant speed to your left? Well, the track. The track pushes straight up on Bertha. That's the normal force. She's moving to the left, which means the friction force applied by the track acts to the right. And then I'm touching Bertha. I was pulling her along. So we'll call that the force of Greg on Bertha. What else was touching Bertha? Nothing. Let's go to Edna. Edna, well, we'll go to Edna in a moment. Hold on. Let me just mention that we are in equilibrium. When something's in equilibrium, up equals down, left equals right. So if we wanted to, we could say the normal force here is MBG, and the force of Greg is equal to the force of friction. Great. Now let's talk about Edna. First of all, Edna has a weight. What is touching Edna? Not the track. The track is not touching Edna. But Bertha is touching Edna. Bertha is pushing Edna upward. I'll call that FB for the force of Bertha on Edna. What else is touching Edna? Well, what about me? Am I touching Edna? Let's do it again. I ain't touching Edna. I'm only pulling on Bertha. Edna does not have any external object touching her other than Bertha. So the only forces she feels are the force of the earth pulling her down and the force of Bertha pushing her up. Since I'm not touching her, there is no force of Greg. Since she's not touching the track, there is no force of the track on her, so no friction force. That's it. Well, wait. Can't Bertha provide a friction force? All right. Let's talk about that. Edna is in equilibrium. She is moving to the left at a constant speed. So therefore, the force of Bertha equals her weight. That you all understand. We must have equilibrium in the horizontal direction. Left forces must equal right forces, if there are any. You said, what about the friction force of Bertha on Edna? Can't there be a friction force of Bertha on Edna acting this way or that way? Well, if there were, then there'd have to be a force in the other direction because she's moving at constant speed. Constant speed requires balanced forces. So if Bertha is pushing Edna that way and she's moving at constant speed, what is keeping her at constant speed? There has to be a force this way. There's not. If the friction force of Bertha on Edna is pushing that way, then that would cause her to speed up or slow down that way. No. As she's moving at constant speed, there is no other force acting on Edna. No force is necessary for motion. It's like if you're in a car in a straight line on the freeway. When you're speeding up onto the freeway, you can feel the back of your seat pushing on you because you have an acceleration forward. Therefore, there's the force of the back of the car seat on you. When you're slowing down, the net force is backward, so you can feel the force of the seatbelt pushing you. But when you're moving at constant speed, then it's almost as if you were just not in the car at all and you were just sitting there, not moving at all. Because forces cause acceleration, not motion. If you can understand that, then you understand everything you need to understand about Newton's laws. It is time, ladies and gentlemen, to take questions. If you would like to give me a question, at Jacobs Physics is where you go. Isn't Edna on Bertha? So wouldn't there be a force exerted by Edna acting down on Bertha? Oh, crap, you are correct. Mr. This is at beta theta stigma. You're correct. I forgot that one. There is the force of Edna on Bertha acting downward, and the normal force is mBg plus Fe. Thank you. Forgot about that one. Yeah, that's right. That's right. Sorry. VPN Breaknose says, if you let the rope connecting the two objects over the edge of a table instead, would that be the same as using a pulley? In other words, over here, if I just take this pulley off entirely and let this thing happen over the edge of the table, it's still going to work. Different acceleration, though, because now there is considerable friction between the rope and the edge of the track. That considerable friction is going to cause energy to come out of the system. You could do an energy analysis and show that that will change the acceleration to something smaller. If I did the net force approach, then I would say that the net force is no longer just the mass of that thing times g. The net force is that minus whatever friction force there is acting between the track and the rope. That is a good question. Yes, and thank you, Dr. Chemistry, for mentioning that the force of Edna on Bertha, this one, is a Newton's third law force pair with the force of Bertha on Edna, this one. Let's see here. We got a couple more minutes. How do you know that tension is 1 Newton or 1.1 Newton? I don't know which experiment you're referring to. If you're referring to this first one where I had the rope over here, I told you the tension was 1.0 Newtons to start with. Oh, are you talking about this one? How do you know if the tension is 1 Newton or 1.1 Newton? You don't. You have to do the math. So remember we did 2 free body diagrams and you had 2 equations and I stacked them up and I canceled those tensions? Well, I found the acceleration was 0.48 meters per second per second. Now, just pick one of those 2 equations and plug in that acceleration, solve for tension, and Bob's your uncle, you got the answer. Try it. I don't have a device to measure the tension this time in this experiment, but you could calculate it. Is there a set equation for tension we can memorize, asks A. No, there's not. Tension could be anything. It's kind of like asking, is there a set number of meters per second that all objects will be moving? No. A tension, this equation where we say Fn equals mBg plus Fe, that's not something to memorize. That's something that I got from the free body diagram. I said in equilibrium, since Bertha is neither burrowing into the track nor lifting off the track, up forces equal down forces. That's how I got that equation. Similarly, when I did this problem, the tension, when I said mg minus t equals ma, that's not an equation for tension. That's something that I got using the free body diagram that applies to this specific situation. To try to memorize an equation for tension is kind of like saying, I'm going to memorize all the possible speeds that a car could have. 1 meter per second, 2 meters per second, 3 meters per second, 4 meters per second. Yeah, you see what I mean? It's a good question, but no, you don't. Let's see. 1 or 2 more. Daniel Z asks, how would I know whether the tension is the same throughout the rope if the pulley had mass? If the pulley has mass, then Jacob's law of tensions does not apply. The tension is different on each side of the massive pulley. The reason for that is because in order for the pulley to speed up rotationally, there must be a net torque on the pulley, and that net torque must be caused by differing tensions on both sides of the pulley. That's not really something that's that important. When we have two-body problems on the AP Physics 1 exam, usually you could ignore the mass of the pulley, and we will certainly never be asked to mathematically determine the difference in tensions and what is these two tensions. Never mathematically. We might need to understand why the tensions have to be different in terms of net torque equals I alpha, but we will never have to do any solutions for those tensions numerically. And one more. Jaden Ha says, is it still wrong to draw a friction arrow if we know that friction is negligible? Yes. Should we draw an arrow for the force of Jupiter on this cart? Because, well, Jupiter is a massive object. By GMM over D squared, Jupiter is applying a force on this cart. So why didn't I draw the mass of Jupiter? We must simplify. An obsession with precision is the enemy in AP Physics 1. If I drew these forces to scale, which I never do, I don't care about that. But if I did draw the forces to scale, then the tension of the rope might be like this, and the negligible friction force might be like that. So don't bother drawing it. If I wanted to draw the force of Jupiter, it might be like that. That doesn't mean that the force of Jupiter isn't there. So is the force of the moon, the force of Mars. But when a force is negligible, that means ignore it. That means don't draw it on a free body diagram. That would be wrong. Anything that you know not to be important, don't draw it there. Simplify. This is what research physicists do. They make the simplest assumptions, and then only if that assumption doesn't work experimentally do we then go back and revise our model and say, hey, there's got to be something else to take into account. All right, that is enough of that. I'm going to share the screen for the problem for tomorrow. Josh is back with you on Thursday and Friday of this week. I have you Wednesday and Thursday of next week, but you're going to get a whole bunch of Josh, just like you got a whole bunch of me last week. And he is going to be talking about conservation of linear momentum tomorrow. He's going to start with this problem, a student on a raft. This is a lot of fun. See if you can do it. He will start tomorrow's class with this problem. Until then, I really am enjoying my time with you all. I hope you'll go watch this on archive. I will be on Twitter. Give me 5 or 10 minutes to finish up here, and then I will be on Twitter until about 2 o'clock, taking questions, stories, or comments and replying to anything you have to say to me. For my friends Edna and Bertha, this is Greg Jacobs saying so long, everybody. Say goodnight, Edna.